Hello again. I hope you're doing well. This is we continue with trigonometry, chapter 6. So let us get us started. I'm going to start where last time we stopped at inverse trigonometric functions. So we are going to talk about inverse trigonometric functions. You know about 6 trigonometric functions. And now we are going to talk about the inverses of them. That means we go backwards, right? Now here is a historical fact here about an astronomer, Middle Eastern astronomer called Habash al-Hasib. And the pictures you see here come from a book I'm going to show you in a second. But basically what they did, if you put a rod on the wall vertical like that, and the sun shines on it, obviously it's going to have a shadow here. And the question is, what is the angle that the sun rays make with the horizontal, right? So that's the question that they wanted to answer. And that is the same angle as this angle right here, of course. And if you think of ratios, we know the tangent of this angle would be opposite over adjacent, so it's s over 1, so it's just s, right? And if you put the stick vertically on the ground this way, and then you want to measure that angle, well, that angle would be the same as this angle here, right? Then cotangent of this would be the t over, let's say, the length of the stick or rod we assume to be 1, right? So this way, make it easy. That's 1 unit. And this is based on that 1 unit. So if this is 1 unit, what is this? It's like, it's related to that. So t over 1, so just t would be cosine alpha. Right? So what is alpha? What is alpha? I mean cotangent alpha. So what is alpha? How do we find alpha? Well, it looks like in solving equations, if you have cotangent alpha equals to t, then we have to basically get rid of this. Now, obviously, we are not going to divide by COT, right? CO doesn't make sense. You're not in middle school. In middle school, somebody would do that, right? Well, even if you do that, then what would t divided by COT be, right? What is that? All right, now we're going to get rid of cotangent using inverse of cotangent. Okay, and inverse of cotangent is not 1 over cotangent. 1 over cotangent is what? Is tangent. That's reciprocal, it's not inverse. So by inverse, we mean a function that cancels what cotangent does. So it undoes what cotangent does. Okay? So in this kind of situations, we need inverse trig functions. And so this is the book. It's called The Crest of the Peacock, and is by George Joseph. He's an Indian-British writer. And this book is about non-European roots of mathematics, history of mathematics. Lots of mathematics was developed in other places other than Europe. And before Europeans started colonizing other people, they actually admitted that lots of knowledge that went to Europe went from East and other places, like algebra and arithmetic. In Europe, Romans, they had Roman numeral, right? And it's very hard to deal with, operations on Roman numerals. So the system base 10 went from East to Europe. And that was algebra, and that in 1202 by somebody called Fibonacci. He wrote a book called Liber Abaci, which means Book of Calculations. And he took algebra and basically base 10 to Europe. And of course, nobody cared that much at the time. Europe was going through dark ages. But in few hundred years, they started using those algebra and base 10 system. And that's what the whole industrial revolution was based on. You need science, you need mathematics to do that. That's where it comes from. So he talks about that. You can read this book. It's a very interesting book. So these pictures come from this book. And that's why we need inverses. So this process requires undoing what trigonometric functions do. And these functions that undo what trigonometric functions do are called inverse trigonometric functions. And remember, in algebra, if you want to find the inverse of a function, we are going to have to, first we have to prove that the function is one-to-one. Because if a function is not one-to-one, right, let's say we have x squared, that's not one-to-one. One-to-one means it passes the horizontal line test. And this doesn't pass the horizontal line test. So this function is y equals to x squared. So if we were to find the inverse of that, we would have to switch x and y and solve for the new y. So this new y would be plus and minus the square root of x. And obviously, this is not a function because it's got plus and minus. So x squared, if you think of it as a machine, takes a number and squares it, right? Now, if you put a negative 2 here, you get 4. But if you put a 2 here, you also get 4. Now, if you want the inverse of this function, right, that means you have to put 4 in here, and what should come out? The input. But there are 2 input values that go to 4. So there is a question mark here. Which one was it that we squared to get 4? We don't know. So there's confusion here. So we like functions that are one-to-one. Functions that are one-to-one, they are either decreasing or they are increasing. Now, if a function has both parts, then it's not going to pass the horizontal line test. That means it's not one-to-one. Which means that if you take the inverse, like I did here, the inverse will not be a function. Okay? So that's the idea. Now, what do we do if we have a function that is not one-to-one? Let's say we have y equals to x squared and is not one-to-one. What do we do? Well, we can make it one-to-one. If you give me a second, I can turn off a program behind here. Is doing some usage of my CPU. Let's see if I can find it. Well, yeah, it went away. Okay, so how do we make it one-to-one? Well, you know, x squared has decreasing part and has increasing part. So we can just erase one part of it. Well, we can't do that. You have to do it algebraically. So algebraically, all I have to do is restrict the domain to be all positive numbers. Then we only want x squared when x is greater than what? Greater than 0. So we only get that part. And if you only think about x greater than 0, then we can find the inverse of this. And the inverse of this would be, of course, square root of x, right? So the inverse would be square root of x, which if you graph it, looks like that. So this is the square root of x, and this is x squared. You also learn in algebra that inverses, the graphs of inverses, are symmetric with respect to y equals to x. They're symmetric. So you see, let me make it a little bit bigger. So if x squared looks like this, square root of x is going to look like this, and this line right here in the middle that cuts this into two images that are reflections of each other, that is y equals to x. And that is always true. if you have two inverse functions, they're symmetric with respect to y equals to x. And the reason is that to find the inverse of a function, we have to switch x and y. And if you switch x and y, that's what you jump on the other side here. So that is y and x compared to that, right? So now the points on the y equals to x don't go anywhere. So for example, this point right here, they have in common. That is 1 squared and a square root of 1. They're both the same, right? So they have that part in common. So if there is a point where x and a y are the same, if you switch them, well, you don't go anywhere. The point stays there. Okay, so now for trigonometric functions, we see that none of them is actually one-to-one. Neither sine nor cosine nor tangent, none of them. So what do we have to do? Well, we have to decide. Remember, a one-to-one function is either increasing or decreasing. So what we have to do, we have to pick a part, let's say this part of sine, that is always decreasing, or we have to pick a part that is always increasing, like for example this part right here. We cannot take the whole thing because then the inverse is not going to be a function. So cosine, the same thing, you see, it doesn't pass the horizontal line test, right? You see, it doesn't pass that. So what do? We pick a part of it, and we don't have to think too hard about picking which part because people have already done that for us. So we have to pick a part that includes 0. So for sine, we're going to pick this part from here to here, and that is negative pi over 2 to pi over 2. So we are going to restrict the domain of sine only in this region and find the inverse of this. The inverse really doesn't have any formula, it just has a definition. It just has a definition, which means that the inverse of this, we're going to call it F inverse, and the notation for it is sine, and we put a negative 1 up there to call it the inverse of sine. Now, very important, that is not the same as 1 over sine. Even though we use the same notation, it's not the same. I believe I forgot the name of a mathematician who actually started this notation, but that doesn't mean 1 over sine. It just means sine inverse. 1 over sine, of course, you know, is cosecant, right? So don't confuse it with 1 over sine. Now, could it ever mean 1 over sine? Well, we usually don't do that, but yes, if negative 1 is actually a power, if we are doing something with powers of sine like that, that is actually negative 1. But if you see it over here, that is never power of negative 1, is always inverse, okay? All right, so that's the inverse, and it doesn't really have a formula. It just says that we want to reverse the process that sine actually was involved in, right? So for example, sine takes, let's say, pi over 6, which is 30 degrees, and give you 1/2. Gives you 1/2, right? That's sine x. So sine inverse is going to take 1/2 and give us what? And give us pi over 6. That's what sine inverse is going to do. So we define them as the inverse process of trigonometric functions. So let's start with sine and cosine. Again, we're going to restrict the sine in this area from negative pi over 2 to pi over 2, including negative pi over 2 and pi over 2. For cosine, the restriction is from 0 to pi. And notice that from 0 to pi, cosine is decreasing always, so it's 1 to 1. And for tangent, also we see is 1 to 1, is not 1 to 1, so we're going to pick from, just like sine, we're going to pick from negative pi over 2 to pi over 2, but there is a little typo here. These equality are not included here. I have to fix that. Okay, because tangent is not defined at negative pi over 2 and pi over 2. Okay, so let's do that. So here is the sine. Now remember, sine, of course, this red one is sine. It goes forever this way, and also it goes forever this way, right? But we don't want that part, and we don't want this part. We only want sine from what? From negative pi over 2, which is negative, negative 1.5 something, 1.4 something. So here's the sine right here, and then the other part of it. So it's just like so close to its inverse. It's so close to y equals to x. So that's what that is, right? Now, if you think about it, close to 0 sine of an angle and an angle are very close. They're very close to each other. Let me do it for you. So if I go to mode radian, I'm in radian already. Okay, so if I do sine of, let's say, something close to 0, 0.1, right? Let's do 0.1. So what is sine of 0.1 radian is 0.0999, right? Is very close to it. That means if I'm close to 0, right, sine of x is approximately the same as x. Okay? I think that program showed up in the background again. Let me see if I can see it and get rid of it. Where did it go? There we go. See if I can see it. Where is that program coming from? It's Skype. Let me get rid of that first. Tablet services. This one right here. What is that? Oh, that's my video program. Okay, that's good. All right, so let me get the calculator back, and you see, oh, we don't need it anymore, but you see the numbers are really close. So that means that when I'm over here, close to 0, right? When I'm over here, this sine is right below that line, y equals to x, right? So at 0.1, y equals to x is 0.1, and sine is a little below it, just a little. It's so close you can't see it. Can't see the difference. Okay, so this is the red one is sine. Let's pick these 3 points. This one right here is negative pi over 2, negative 1. This one, b, is 0, 0. And that one is pi over 2 and 1. So what do we have to do to find the inverse? You just have to switch them. So negative 1, negative pi over 2, 0, 0, 1, pi over 2. So we put these blue ones right there, right here, and right here. 0, 0 stays the same, right? 0, 0 stays the same. And we connect these, and you see the graph of sine inverse. So that blue one is actually f of x, f prime of x, which is not f prime, f inverse of x, which is inverse of sine x, that blue one, right? So sine x kind of looks like this in that part, and the inverse of it is kind of close like that, and over here it's kind of like that. So that's the inverse of it. Inverse sine and sine in the restricted domain, right? And the restricted domain is negative pi over 2 to pi over 2. All right, now, so that's the graph of sine inverse. Now, what does that mean? So when I write sine inverse of, let's say, 1/2, what is the question we are answering here? The question here we are answering is this. What is the angle in the restricted domain only, because we work with sine only in that domain. So what is the angle in this restricted domain whose sine is 1/2? That's the question you're answering. Whenever you see a structure of sine inverse, think of it as an angle. So it's an angle. The answer to this is an angle. What type of angle? Is the angle in where? Only in this region, right here, whose sine is 1/2. And we know in this region, right here, what's an angle whose sine is 1/2? 1/2 is like halfway here. Well, we need a point on the unit circle whose y-coordinate is 1/2. And that's the point. That's the only angle. And we know, of course, that is what? That is 30 degrees, right? Or pi over 6. So the answer to this is pi over 6 or 30 degrees. Usually we work with radian, and occasionally it's good to think of degrees to understand where the terminal side is, because it's more intuitive to think of degrees if you want to know where the terminal side is. Okay, so that's what this means, and that is the graph of it, and that is the table of values. You can add some more if you want to, but that's sine inverse. Now, remember to, when we find the inverse, what do? We switch x and y. And if you switch x and y, then the domain and range also, they get switched, right? So the domain of sine inverse is actually the range of sine, which is -1 to 1. Remember, we didn't restrict the range, we restricted the domain. So the range of sine becomes the domain of sine inverse, and the restricted domain of sine becomes the range of sine inverse. Notice the sine inverse goes from pi over 2 to negative pi over 2. That's what the range of sine inverse is. And the domain of it, notice that is from -1 to 1. That's the domain of the blue graph, right? Okay, and that's the range. All right, so that's all there is to sine inverse. Really, there's nothing to it. You just have to practice. So explain the meaning of arc sine 0.5. Now, arc sine is even better notation for what? For sine inverse. So basically, arc tells you if we have an angle, right? The arc is the same as the angle, right? So basically, arc sine of 0.5 means what is the arc? What is the angle whose sine is 0.5? So it's a better notation. You don't confuse it with 1 over sine, right? So we're going to leave it like that. Arc sine 0.5. So what does that mean? Again, what is the radian measure of an angle in this whose sine is 0.5? The answer is pi over 6. Okay? Again, we're talking about what? Only in this region. Why? Because this is the restricted domain for sine. So the answer to sine inverse is a unique answer. It doesn't have many answers, it has only one, right? Because we decided to do that, so we don't get confused. All right, so evaluate the expression sine inverse of the square root of 2 over 2. Again, what's the question we are answering? What is the radian measure of an angle, of the angle, because there's only one. What is the radian measure of an angle, right? So it should be the angle. I got to fix that too. In what? In here, whose sine is what? Square root of 2 over 2. So the answer is pi over 4. Okay? It's okay if you see an angle, but, that doesn't make that much of a difference because we know there is only one angle. Okay, and the answer is pi over 4 because we know that sine of pi over 4 is square root of 2 over 2. Now, with the calculator has inverse on it. You see inverse sine right here, inverse cosine, and inverse tangent. So if you want to work with inverses and you want to know exactly what the angle is, you can put it in radian, put it in degree, right? And just put sine inverse of, let's say, square root of 2 divided by 2, right? Like that. And you see it's 45 degrees, the answer. And the calculator always gives you the correct answer in the right region because it's programmed to do that. Okay? Calculator always looks in the right region for the angle whose sine is what? Square root of 2 over 2, and gives you the correct one. But some of these you can easily do by hand, right? Okay, so that's it. Now we know from algebra that if you take two inverses, let's say f of x equals to x squared, and f inverse is the square root of x for only x greater than or equal to 0, right? Now, if you take the square root of x and input it into f, you get x, right? And if you take x squared and input it into that, you get x, because x is positive. So square root of x squared is x, and also square root of x to the second power is x, right? Notice what that is. That is f inverse of f of x, right? And what is that? That's f of f inverse, right? That's what that is. So from algebra, we know that if two functions are inverses, then these two have to be true, right? Now, of course, this is true when x is in the domain of f inverse, and this is true when x is in the domain of f, right? Otherwise, this doesn't make sense. If x is not in the domain of f, you can't get anything out of here, right? So we can apply this to sine and sine inverse. So if you take sine of sine inverse of x, you get x. Now, this is true only if x is in the domain of sine inverse, which is, remember, negative 1 to 1. So if x is in this interval, then this is true. Now what about this one? Well, this one is only true if x is in the restricted domain of sine. If it's not in the restricted domain of sine, this doesn't work, right? And I've given you an example here where the answer is not 3 pi over 4. Why? Because 3 pi over 4 is not in this region. It's supposed to be here. If it's here, the answer is just whatever it is, right? For example, if this is pi over 4, the answer is pi over 4, but not here. What is the answer? Well, the answer is the angle in this region that has the same sine as what? As this angle. And of course, that would be this angle here, right? Which is what? Reference angle. So the answer would be that angle right there, which is 45 degrees, right? All right. So now with the calculator, you get the correct answer, but you need to understand why, okay, in this course. I know we have a calculator, we can do this. First of all, notice that there are 3 inverses missing on the calculator, so you got to understand even if you want to use the calculator. We don't have secant inverse, we don't have cosecant inverse, we don't have cotangent inverse on the calculator. So you got to understand what's going on here. So this angle here, only the answer is x, only if this angle is and this x value is in this region, which is the restricted domain for sine. All right. Now, what about cosine? Well, we said the restricted domain for cosine would be from 0 to pi. See? From 0 to pi. We pick this part of cosine. And notice that there are 3 points here. We can take these 3 points and flip, just switch x and y. And notice over here, I switched x and y. And we get arc cosine. So arc cosine of 1 is 0. Arc cosine of 0 is pi over 2. Arc cosine of negative 1 is pi. So we graph the blue ones, that one, this one, and this one. And notice these are just reflections. See that? Over what? Y equals to x. So that blue graph is a graph of arc cosine. And this point they have in common. There is a point that they have in common. What is that point that they have in common? Is a point that cosine x and the cosine inverse are the same, right? Right about here. That they intersect. So if you switch them, it doesn't go anywhere, it stays there. Okay, so the blue one is inverse cosine or arc cosine, and the red one is cosine. Restricted domain 0 to pi, and you switch them, you get the domain and range for cosine inverse. Okay, and then you can stop the video and take a look at this and make sure everything makes sense to you. So what do we mean when we write cosine inverse 1/2? We mean we're looking for the angle in what? In 0 to pi, in this region here. We're looking for an angle in this region whose cosine is 1/2. Now in this region, what's an angle whose cosine is 1/2? 60 degrees. That's the only angle in this region. So the answer to this is 60 degrees, or pi over 3. Okay? And this should be an r here for x is in 0 and pi. Okay? All right, so this is tangent. Again, remember, we restrict the tangent in negative pi over 2 to pi over 2. And the domain of the range of tangent is all real numbers, this red graph here, right? And remember, tangent has vertical asymptotes. X equals to negative pi over 2, right? And x equals to, and the colors, I got them mixed up, that's okay. This blue vertical asymptote should be red, go with the red, but I made them blue, that's okay, I'll fix it later. But for now, they're correct, it's just the color is a little maybe confusing. So this should be red, okay? And those x equal to negative pi over 2 and pi over 2. So what happens to the vertical asymptotes? Well, what happens to them is that since we switch x and y, they turn into y equals 2. So the vertical asymptote, the two vertical asymptotes tangent, these two blue ones here, turn into what? Horizontal asymptote, because we change x to y, and they're going to be this one right here and this one. Okay? And that's there was the horizontal asymptote for what? For tangent inverse or arc tangent. Now we can take these 3 points on tangent, which is negative pi over 4 and negative 1, 0, 0, and pi over 4 and 1. And just switch x and y to graph the corresponding points, which are not here. I'll put them here. there, and one of them stays the same. So that would be the graph of arctangent or tangent inverse, the blue one, right? So basically what we have is the graph of tangent that looks like this, and graph of its inverse, which is going to look like what? Look like that. So, all right. So again, the domain and range switch, right? The domain here becomes a range. As you see it here, that's the range from negative pi over 2 to pi over 2, not including negative pi over 2 and pi over 2. And the domain becomes all real numbers, right? All right. So now, example, evaluate the expression tangent inverse of 1. What are we looking for? We're looking, what is the radian measure of an angle in the restricted domain of tangent whose tangent is 1? And we can go to degree on the calculator and put tangent inverse of 1, we get 45 degrees. And we know this is pi over 4, right? So that's what tangent inverse is all about. All right, and also this idea is true for all of them, right? So tangent of, I think we maybe forgot to do it for cosine. Let me do it for cosine. So cosine of cosine inverse of x is x, only if x is in the domain of inverse, which is negative 1 to 1. And this one is true only if x is in the restricted domain of cosine, which is 0 to pi. Now for tangent, this is true only if x is in the domain of tangent inverse, which is all real numbers. That means this is always true, no matter what x is. And this one right here is true if x is in the restricted domain of tangent, which is negative pi over 2 to pi over 2, right? All right, so here is cotangent. Again, cotangent is not 1 to 1, so we have to restrict the domain. We restrict the domain to 0 to pi, not including 0 and pi. And we know cotangent has, again, vertical asymptotes at 0 and at pi. So that's x equal to 0. And that one is x equal to pi right here, right? So that's one period of one cycle of cotangent. And now to graph the inverse, we take 3 points. This one, looks like I got the points correctly, color. So these are 3 red points right here. And then we switch x and y, we get these, and these are going to be on the cotangent inverse or arc cotangent. See? And we connect them, and we know this approaches its horizontal asymptote. So these turn into y equals to 0 and y equals to pi, which is that one and this one. That's y equals to 0, and this one is y equals to pi. Right? So that's the graph of cotangent inverse or arc cotangent. Same is true for cotangent. That means if you have cotangent inverse of x, this only works if x is in the domain of cotangent inverse, which is all real numbers, so it works. This works only if x is in the domain of cotangent, which is 0 to pi, restricted domain, right? So remember, for sine and tangent, the restricted domain would be negative pi over 2 to pi over 2. For sine, they're included, and for tangent, they're not included, right? And for cosine and cotangent, the restricted domain would be 0 to pi. For cosine is included, and for cotangent, they're not included, right? So those are the restricted domains. Okay, now what does this mean? Again, it means what's the radian measure of an angle in this region whose cotangent is the square root of 3. Okay, and that is pi over 6. Now, remember on the calculator we have sine inverse, we have cosine inverse, and we have tangent inverse. But we don't have cotangent inverse, so how do we deal with it? We're going to see that in a second, okay? So let's look. So we know that cotangent inverse of x is the same as tangent inverse of 1 over x. How do we know that? Because remember, tangent x and cotangent x are reciprocals, but they're reciprocals in the y values, right? The y value of tangent is 1 over cotangent, or the y value of cotangent is 1 over tangent, right? Now, these are not tangent and cotangent, but they're inverses of tangent and cotangent. So that means x and a y are switched, right, over here. X and y are switched. So that means whatever is true for y values is true for x values here, for domain values. So that means cotangent of x, cotangent inverse of x is the same as tangent inverse of 1 over x. But since we choose two different restricted domain for tangent and cotangent, then we have a problem. And the problem is that if, and I'm going to explain it right here, right? It says, note, tangent inverse has range this, but cotangent inverse has this range, which is the restricted domain for tangent and cotangent. So what happens is, these are restricted domains. So when you do this, for values between 0 and pi over, for the positive values inside here, from pi over 2 to pi, that works. That means if x is positive, this works. But if x is negative, it doesn't work, right? If x is negative, then since these two don't match, right, it's not going to work. So from 0 to pi over 2, right, from negative pi over 2 to 0, for these values, so for negative values of x, tangent inverse gives negative values, right, because of the range. Remember what tangent inverse means. It means what's an angle whose tangent is 1 over x, and if this is negative, right, then it's going to what? Is going to look here in the negative numbers for answer. So the answer to tangent inverse would be negative, and the answer for cotangent inverse would be positive, because cotangent inverse always gives you positive answer here. Now, tangent inverse gives you negative answer for some values of x. For what values of x? For negative values. So that means this is not true if x is less than 0. So what we can do to make it true, we can add pi to it. So we can actually do cotangent inverse of x is tangent inverse of 1 over x, and then we add pi to it to be correct. Now, there's an easier way to do that. So for cotangent inverse, we just not use this at all, because it's not always correct. But one thing that is always correct is that, and I gave you an example here why it doesn't work, but one thing that is always true is that tangent inverse of x plus cotangent inverse of x is always pi over 2. Remember we said if two angles add up to 90 degree, then the function of one equals to cofunction of the other one. So if alpha plus beta is pi over 2, then the tangent of alpha is the same as cotangent of beta, or the other way around. Tangent of beta is cotangent alpha. So that means if the input values add up to 90, then the output values are equal. And when we do inverses, we actually switch x and y. So that means this idea, this characteristic that is true for the tangent and cotangent, we have to switch x and y, domain and range, to be true for this one. I know it might be a little vague, but think about it. If the input values add up to 90, then the output values are equal. Here, if the output values add up to 90, then the input values are equal. See? Just exactly like that statement, except I switch the input and output, right? Again, if the input values add up to 90, then the output values are equal. If the output values add up to 90, then the input values are equal. Okay? So this is always true, and it's true for the other function and cofunctions too, and we're going to get to that. So the expression that is really useful is this one right here. So if you want to use a calculator to find cotangent inverse of something, what we do is what? We do pi over 2 minus tangent inverse of x. Right? That's it. So if you want to find cotangent inverse of a square root of 3, now in this case, if a square root of 3 is positive, so we could just book tangent inverse of 1 over square root of 3, which is correct, right? And we can also do cotangent inverse of square root of 3 is pi over 2 minus tangent inverse of square root of 3. You get the same answer. And I did it over here on the calculator in degrees, so you can see it. See, in degrees, I put tangent inverse of 1 over square root of 3. I get 30 degrees. And I did 90 minus tangent inverse of square root of 3. Not 1 over, but the square root of 3. And I got 30. So it's a much easier one to use. In fact, if you want to graph cotangent inverse with a calculator, what do? What do you put in y equals to graph it? We don't have cotangent inverse. So what you put in y equals to graph it is pi over 2 in parentheses minus tangent inverse x. That's how you graph it. Okay, so this works for positive x, right? And it doesn't work directly unless you add pi to it for negative x values. And this always works. So we use this for cotangent inverse. So just subtract from pi over 2. Okay, what about secant and cosecant? Well, secant, again, is not 1-to-1. So remember, secant is related to what? Cosine. So restriction is from 0 to pi. But since secant is 1 over cosine, right? Then cosine cannot be 0, and cosine of pi over 2 is 0. So we have to exclude pi over 2. So secant restriction is similar to cosine, except pi over 2 is not included. So we have to divide it into 2 intervals, 0 to pi over 2, pi over 2 to pi. And the range, we already know the range is, all real numbers except the numbers between -1 and 1, right? And we know in this restriction, in this restricted domain, it has one vertical asymptote. Is the red one right here, see? That is one cycle of secant. Now we can put a bunch of points here, right? We can put this point, that point, maybe this point and this point. 4 points. And then switch x and y to find the points on arc secant and graph them. I did that with the blue one. You can stop the video and make sure these actually are the points that are graphed here. And this vertical asymptote, which is at x equals to pi over 2, this one right there, turns into y equals to pi over 2, which is that one right there. And that's what the graph of secant inverse or arcsecant looks like. Now, we usually don't need arcsecant because we can use what? We can use, remember we said the functions and cofunctions are related. So function inverses and cofunction inverses are related. How are they related? Well, this is how they're related. Function inverses plus cofunction inverse equals to pi over 2. That's true for tangent inverse plus cotangent inverse. It's true for sine inverse plus cosine inverse. It's true for secant inverse plus cosecant inverse. These are all true, right? Okay, so now we also know that the reciprocal relationship between cotangent inverse and tangent inverse is true for positive values because the restricted domains are different, right? But the cosine inverse of x, well, we don't need cosine, let me secant inverse. So secant inverse of x is the same as cosine inverse of 1 over x for all domain values. Why? Because secant and cosecant have the same restrictions. Of course, there is a pi over 2 that doesn't work, but we don't need that. We know, I said it's true for domain values of x. So if this number is not in the domain of, cosine inverse, is not here either, so we don't need it. So, and also we're going to look at cosecant in a second, but cosecant inverse also of x is related to sine inverse of 1 over x, again for all domain values. So we can use these two for all domain values, but this one only is good for positive x. So this one, let's say we don't use it, we just use cotangent inverse of x plus tangent inverse of x equals to pi over 2. So to find the three inverses that are not on the calculator, we're going to use these. So for cotangent inverse, we use this. For secant inverse, we use this. For cosecant inverse, we use this. These are on the calculator, right? These three. All right. So we got secant inverse under control, and that's the graph of it. The domain and range switch, right? And the same thing is true for secant. Secant inverse of secant x, all of that is true for secant as well. And for cosecant has the same restriction as sine. Sine was negative pi over 2 to pi over 2, right? But again, there is a number in the middle because this is 1 over sine, and sine x cannot be 0, so x cannot be 0. So it's all numbers between negative pi over 2 to pi over 2 except for 0. That's the restricted domain. And again, we can get the one cycle of cosecant, right? One cycle of cosecant, and switch the 4 points, switch x and y, and you see the blue ones, and there is one vertical asymptote, which is actually the x-axis itself, right? That's the vertical asymptote. It turns into y equal to 0, which is the x-axis. So you see the blue one is approaching the x-axis here and is approaching the x-axis there. Is an asymptote. Okay, Again, you can stop the video and make sure you understand these points, and you can do a bunch of examples to get this under control. So here is the discussion that I had for these three I already gave you. So there is this relationship between function inverses and cofunction inverses. So arcsine, arccosine, arctangent, arccotangent, arcsecant, arccosecant. They have this relationship for all domain values. Now reciprocal relationships again are cotangent of x is tangent inverse of 1 over x, but this is true for x positive, and secant inverse of x is cosine inverse of 1 over x, is true for all x values in the domain, and cosecant inverse of x is sine inverse of 1 over x, okay? So these are the relationship you should know between the inverses, and they're pretty useful, okay? And I explained what I just said in the last slide here. You can stop the video and read it, see if it makes sense, okay? All right, so the reciprocal relationship between sine and cosecant, and tangent and cotangent, and cosine and secant that exists between the range values transforms on the reciprocal relationship between the domain values for the inverses. And this is a complete picture of that. If you want to use this, you have to make sure that if x is negative, you have to add pi to it to be correct. Okay, so here are all of them together, and I got this table from Wikipedia. So these are all the inverses with the definition, with the domain and ranges, restricted domain and ranges. Okay, so that's it. And so we got evaluate the following. Secant, I have something showing up early, but that's okay. So secant inverse of 2, what is that? Well, we can use a calculator. So secant inverse is not on the calculator. So what do we use instead? Cosine inverse of 1 over 2. And that's the answer, 60 degrees. Put it in degrees so you see what the angle is, and then you can convert it to, you can do it in radian if you have to. But in degree, it gives you a better kind of intuitive understanding of what's going on. What about cosecant inverse of negative 2? We do sine inverse of 1 over negative 2, or negative 1 over 2, the same thing. Get negative 30. And secant inverse of secant of 5 pi over 4. Now, if you want to use a calculator to do this, this is what you have to do, right? First, you have to find what? Secant 5 pi over 4, because you don't have a button for this on the calculator. So secant of something is 1 over cosine. So that's what I did. And since I'm in degree mode, I use degree, because 5 times 45 is 225. So I use degrees here. So 1 over cosine 225 is what's inside the parentheses. And then secant inverse, what do we do with the calculator for secant inverse? We use cosine inverse of 1 over this. So I put cosine inverse 1 over the answer. The answer is this number. And I got 135 degrees. Now, if you want to do it by hand, here is how it is done. So first we find secant 5 pi over 4, which is 1 over cosine 5 pi over 4. And cosine 5 pi over 4, remember you have to use what? Reference angle. 5 pi over 4 is over here. So this is pi over 4. So cosine of this is the same as negative cosine pi over 4, right? So it's negative square root of 2 over 2. And 1 over this, you just take the reciprocal. So secant inverse here, secant inverse of this is secant inverse of negative 2 over square root of 2. then this is the same as cosine inverse of negative square root of 2 over 2. And in the restricted domain of cosine, which is over here, in this region, what is an angle whose cosine is negative square root of 2 over 2, which is about right here. So that angle that has that cosine is this angle, which is 3 pi over 4, which we calculator gave us 135. Okay? All right. So now sometimes we can use a little triangle to help us do these. These are not the same. They're two different functions, right? So this is cotangent, this is cosecant inverse. Now, inverses are always angles, right? So to simplify this, we assume this is an angle, right? Let's call it alpha, whose cotangent we're trying to find. What's cotangent of an alpha, right? Now, we're going to assume that this alpha is an angle whose cosecant is negative 3, right? Now, since we don't want to work with negative numbers, we can work with positive numbers only. So we can work with angles between 0 and 90, acute angles. So we always, to do these problems, we draw a right triangle and assume that this angle right here has the same cosecant except absolute value of it. So we don't have to work with negative numbers. So if theta is an angle, instead of alpha, we find theta. Theta is an angle whose cosecant is 3, right? So theta is the angle whose cosecant is negative 3. If cosecant of theta is 3, absolute value of negative 3, then cosecant is what? Is 1 over cosine, so we say 1 over sine. So we say sine of theta has to be 1 over 3. So we're going to set up theta in a right triangle such that the opposite is 1 and the hypotenuse is 3, and then use Pythagorean property to find that side. 3 squared equals to 1 squared plus that. See that? We can easily find that this is 2 square root of 2. Okay, now that we know all 3 sides, we know all 6 ratios. Which one do we want? Well, we want cotangent, right? So cotangent of theta, I know we're working with alpha, not theta, but the only difference is sine, right? Because theta is a reference angle for alpha. So cotangent theta is adjacent over opposite, so it's 2 square root of 2 over 1, which is 2 square root of 2. So that's cotangent. But we don't want cotangent of theta, we want cotangent of alpha, right? So we know that angle whose sine is negative 1 over 3 is in the restricted domain of sine, which has to be here, right? Because that's what, restricted domain for sine inverse is, right? Restricted domain for sine to take the inverse of it. Okay, we also know that its sine is negative. How do we know that? Because we say cosecant is negative 3 alpha. We're not talking about theta anymore. We are done with theta. Theta gave us this rectangle with all the sides, so we don't worry about theta anymore. We worry about alpha because we want to figure out the sine of it. So alpha, we say cosecant of, so alpha is an angle whose cosecant is what? Is negative 3. That means sine of alpha is negative 1 over 3, right? So that means the sine of it is negative and it has to be in this region, right? So if you are in this region and sine has to be negative, well, then you're over here, right? And over here, cotangent is negative. So we have to put a negative right beside this number that we found, and that's the answer. Okay? Again, go over this one more time. We're looking for alpha whose cosecant is -3. Now, if cosecant of alpha is -3, that means sine of it is -1/3. But we're going to think of another angle, reference angle for alpha, which is theta, whose sine is not -1/3, but is +1/3. So here you go. Then we set up this rectangle. Then we have what? We have all three sides. Now we find cotangent of theta instead of alpha, right? And then that gives us the value of it. Then we figure out what the sine is based on where alpha is, which quadrant it is in. And we figure out that it has to be negative. So it's -2 square root of 2. Let's do one more. So sine of tangent inverse of -3/4. Again, we think of alpha to be what? Alpha is an angle whose tangent is what? -3/4. Now we're going to think of theta as an angle whose tangent is what? +3/4. So that means opposite 3 and adjacent 4. And then this has to be 5 again using Pythagorean property. So what do we want? We want sine of alpha. So we find sine of theta and then figure out the sine, because theta is a reference angle for alpha. This is alpha, and that's theta is the reference angle for it. So what's sine of theta? Well, sine of theta is 3/5, right? Now we have to figure out the alpha. Where is alpha? Well, we know that angle whose tangent is -3/4 is in the restricted domain of tangent, which is this area. Again, we are working with this area here. We're looking for an angle here. But also, we know that its tangent is negative. So if the tangent is negative, it has to be, again, over here. So alpha is over here, so because the tangent is negative. And over here, we know sine is negative. So that means we have to put a negative here, and that's the answer. All right, stop the video, take a look at this, and see if you can kind of follow this and get the same answer. Now, here's a summary of all of them that we talked about with the restricted domains and where these statements actually are true, right? So again, stop the video, review this for yourself, make sure they all make sense to you, and then we're going to move on, okay? So here you go. Now, this in calculus is useful to turn trigonometric expressions into algebraic expressions and back. Now, what do I mean by algebraic expression? I mean expressions that you can use variables and numbers and operations, right? And operations, maybe raising to power and taking a square root or cube root, nth root. If you use operations and variables and numbers, right, to put an expression together, then you have an algebraic expression. These trigonometric functions are not algebraic because you cannot make sine x using what? Variables, numbers, and operations. They're called transcendental functions. So trigonometric functions are transcendental functions. Same is true with exponential that you learn. Those are not algebraic, they are transcendental functions. Okay, so how do we convert these things to expressions? Well, we're going to assume that arc sine of x is an angle whose sine is x. Now, how can sine of an angle be x? Well, that means opposite over hypotenuse has to be x. So we can put x here and put 1 here. Then this is an angle whose sine is x, right? And using, again, Pythagorean property, we can find this side. Now we have all 6 ratios of theta. Cosine would be this over 1. Tangent would be this over this. Cotangent would be this over that, and so forth, right? That's pretty useful. And again, I have only one of them here when arc sine is written in terms of sine, cosine, and tangent. So if the sine of the angle is x, right? So sine of this angle, this is an angle, right? Sine of it is x. So that's it. What is cosine and tangent? Well, we get it from this triangle. And then the other 3 are reciprocals. We can just switch them, right? We can find it. So that means with this trick, we can turn these into algebraic expressions for the 6 ratios, right? Now I have here from Wikipedia all of them, all the possibilities. For arc sine is the first row. Arc cosine, that means we're looking for an angle whose cosine is x. So we put the x here and we put the 1 here. And then we use Pythagorean property to find that one. Now we can write all the expressions using what? Using that triangle. Again, the sign depends on which quadrant we are in. We are talking about just positive, theta here. And we can figure out which quadrant we are in. We can use negative or positive or both, right? Here, we just find the values, and the values are correct here. Okay, and tangent, what's an angle whose tangent is x? So x has to be here, 1 has to be here, and then we figure that out. Now we can write all 6 ratios. We only need 3 of them because the other 3 are reciprocals. And what about our cotangent? We're looking for an angle whose cotangent is x, so we put the x here and we put the 1 there. What about arc secant? We're looking for an angle whose secant is x. That means whose cosine is 1 over x. So we put 1 here and we put x there. And then arc cosecant is x. We're looking for an angle whose cosecant is x. That means whose sine is 1 over x. So we put 1 here and we put x here. And then figure it out. Okay? That's from Wikipedia, and you can take a look at it. Okay, so here's an example. Rewrite in terms of an algebraic expression of x. Find the domain and range of tangent of cosine inverse of x. So we're going to think of cosine inverse as an angle whose cosine is x. So here you go. X here, 1 there. So this has to be square root of 1 minus x squared by Pythagorean property. So cosine inverse is alpha. Let alpha be the angle whose cosine is x. We draw a right triangle to help us see the trig ratios, then decide the sign of the ratios, right? So we simplified it. Instead of calling it theta, we just call it alpha and then figure out the sign, right? It's easier. So cosine alpha has to be x, right? We know that the angle whose cosine is x is in the restricted domain of cosine. So alpha equals to cosine inverse of x for x between -1 and 1, of course. We know the domain of x has to be -1 and 1. But we know that the tangent, right, is undefined for alpha equals to pi over 2. So alpha cannot be pi over 2. That means what? X cannot be 0. So tangent alpha would be tangent of this, which by the triangle is just that over this, right? And for x is between x in this interval, right? 0, of course, from the algebraic expression, you know that 0 is not in the domain because it's in the denominator. But we also know because this is an expression coming from tangent of something, and we know this something, which is the input, cannot be pi over 2. And how do we know we have to only worry about pi over 2? Because in the restricted domain, there is only one number whose tangent is not defined, and that's pi over 2. And that makes x 0. right? All right, so again, stop the video and see if you can figure out what we did here is correct. Here's another example, cosine of sine inverse of x over 3. Again, we assume that sine inverse is the angle whose sine is x over 3, and we find this. Now we have to worry about the sine, right? So cosine alpha equals to this because it is adjacent over hypotenuse. Now we know that the angle alpha, whose sine is x over 3, is in the restricted domain of sine. So alpha equals the sine inverse of x over 3. For x over 3 has to be between -1 and 1 because domain of sine inverse is -1 to 1. And if you multiply everything by 3, you get x has to be between -3 and 3, right? Now, cosine has to be positive in this right here. So cosine alpha is greater than or equal to 0 in this restricted domain, right? See, in this restricted domain, cosine is always positive. Cosine is the x value, so it's positive. And we know that that has to be in this area, and cosine is positive in this area, so that means we don't need to worry about then putting a negative here. We just use square root of 9 minus x squared over 3. And x has to be between -3 and 3. Okay? If you do few of these, you get used to it. Pretty useful. Here's another one, tangent of secant inverse of x. Again, we assume that secant inverse is an angle, alpha, whose secant is x. That means whose cosine is 1 over x. So whose cosine is 1 over x, and we figure this out from Pythagorean property. So we have the rectangle. We can get the values. What's the tangent of this? Tangent is opposite over adjacent. So that's the tangent. But you have to figure out the sine. We know that the angle alpha, whose secant is x, is in the restricted domain of secant, which is that, right? So tangent is positive in this interval, and tangent is negative in this interval. So that means we have to pick the positive square root of x if alpha is in 0 to pi over 2, and we have to put a negative before it if alpha is in pi over 2 to pi, right? So that's how we're going to get this. We got two different expressions depending on what alpha is, where alpha is. All right, and here is another example where we can apply these things to solve inverse equations. So suppose we have arc sine x minus arc cosine x equals to pi over 6. How do we solve for x? And we're going to talk about solving. We talked about solving equations, but we didn't do anything with inverse in it. So here we can use this trick. We know that arc sine plus arc cosine is pi over 2, right? And we know we are given this equation, so we're going to combine it with the other equation, just add them together, and we end up with this. So 2 arc sine equals to 2 pi over 3. So arc sine is pi over 3 if you divide both sides by 2. So arc sine has to be pi over 3. We know sine has to be square root of 3 over 2, right? So arc sine is pi over 3. So sine of arc sine is basically x equals to square root of 3, right? Square root of 3 over 2, I mean. All right, so here is an example of solving using right triangle. Example of using trigonometric ratios to solve right triangle is a very easy one. if cosine of theta is 9 over 12, then what is theta? Well, you can easily use a calculator to get theta equal to 41.4, right? All right, so I'm going to stop here, and I'm going to see you in the next video. If let me go over here for chapter 7, okay? So I see you in the next video. Take care.